Okay, guys, in this section we are talking properties of logarithms. The main goal is to apply these properties of logarithms. And then in the next section we'll talk about how to use these properties of logarithms to solve equations. Three big rules. The first rule is the product rule. The product rule says that log base a of m times n is equal to, anybody remember?
Log base a, no, log base a
of
m.
There you go.
Plus log base a of n.
There you go. Now I knew that you had the right thing in mind, but the language counts because the language facilitates thought, right? And when you say a to log base a of a to the m, it kind of sounds like an exponent. And if you go 6 months without doing this stuff, you might start thinking of it as an exponent. The devil is in the details there, and if I sound like I'm being picky or picking on him, that's not what I'm doing, because 10 other students in this class really did think it was an exponent. Okay. Does that look too crazy? Let's prove this one. I won't prove them all, but I will prove this one. Proof. Okay, I'm going to call this guy, I'll call u. Log base a of m, I'll call u. Log base a of n, I'm going to call v. So I'm going to say let u equal log base a of m. Let me make a little more room. And let v equal log base a of n. So you may not know why I did that, but does everybody see what I'm doing? Okay. What's the only thing we know how to do? Really? The only thing we really know how to do from yesterday is convert to exponential form. So on both of these, I'm going to convert to exponential form. And what is, okay, u equals log base a of m is in logarithmic form. What is that in exponential form? Yeah, it's a to the u equals m. Any question there? And then what about this guy? V equals log base a of n. What is that in exponential form? A to the v equals n. And it really is supposed to be a capital M over here, I guess. Okay? Everybody agree with that? Just converting both of those to exponential form? All right, let's multiply m times n. So m times n in terms of the base a, the powers of a I created, m times n is what? A to the u times a to the v. And then using a very familiar rule of multiplying like bases, how do you multiply a to the u times a to the v? You keep the base and you add the exponents. And we're almost there. You get m times n is equal to u plus v. And now guess what we're going to do? This is in exponential form. We're going to go back to log form. And what do you get? What goes by itself? Yeah, u plus v goes by itself because that's the exponent. And then the base of the exponent becomes the subscript on the logarithm. And then the only thing left, the m times n, is your input, which is exactly the input we wanted on the left side. And then what is u, what is v? Well, go back up and look. Oh, u is exactly what we want it to be. U is log base a of m, and v is log base a of n. Can you guys see that? I kind of zoomed out a little bit. So I've got it, right? That's my proof. Log base a of m times n is equal to log base a of m, that's u, plus v, which is log base a of n, and this proof is over. That's it. That's what we were trying to prove, right? So what does the product rule really hinge upon? It really hinges upon that very familiar law of exponents, that when you multiply like bases, you keep the base and add the exponents. The next one's the quotient rule, and it looks much like the product rule. So the quotient rule says, well, I'll bet, let me write the left-hand side, and I'll bet you can fill in the right-hand side. Log base a of m divided by n. How do you think the right-hand side is going to look different from the right-hand side of the product rule? Instead of being a plus here, it becomes a minus. And that's easy to remember, right? Because usually we associate multiplication with addition, because multiplication is for multiplying natural numbers, multiplication is repeated addition, right? And we also associate division with subtraction. So it's not hard to remember. So log base a of m divided by n, that's the input, is log base a of m minus log base a of n. Do you think you need to memorize these rules? Yeah, absolutely. You gotta know them. You could prove that one in much the same way we proved the product rule. So I won't bother showing you a proof to that. And then probably the most important rule for solving exponential equations is the power rule, which says if you have log base a of m to, say, the c power. So let me make this clear, you guys. The input is m to the c power. That's the input on the log base a function. Then, anybody remember? You can bring the c down in front, and you get c times log base a of the input is just m rather, on the right side. So log base a of m to some power is equal to that power times the log base a of the base m, which seems a little crazy, but it's just, I mean, one way to think about it, especially if c is a natural number, one way to think about it is just repeated application of the product rule. I'll give you an example. So, for example, if we had log base, I don't think it matters what the base is, so I'll leave it base a. If we had log base a of x cubed, then I want to show that you could bring this 3 down in front. So here's what I could do. I could think of it as log base a of x times x times x. Whoops, got a little ahead of myself. Isn't that what x cubed means? But then couldn't you apply the product rule to that a couple of times? And wouldn't this be log, so you guys tell me, log base a of x plus log base a of x plus log base a of x. So I'm applying the product rule like 2 different times there. Oh, but then these are all like terms. You can think of this as 1 times log base a of x. This guy is 1 times log base a of x. This guy is 1 times log base a of x. So you're adding 3 of those together. How many do you have? 3 of them. So that's going to be equal to 3 times log base a of x. And you can see that, well, at least for a natural number exponent like 3, that product, or that power rule rather, certainly holds. We can bring this 3 down in front as a factor in front of the log base a of x. Okay? It also, I'm not going to prove this, but it also works for fractional exponents, decimal exponents. Has everybody seen the ln x before? So the input, I'll put in the parentheses, although you don't have to. The input is x and the name of the function is ln. Has everybody seen that before? What does it stand for? The natural log, logarithm natural, right? So what does it really mean? It really means log base e of x, where e is that number we talked about the other day, the base to the natural exponential function, approximately 2.718. Okay, so don't let the ln here scare you. It's just the ln, natural log of the input is z cubed divided by the square root of x times y. So I want to remind you how to expand. So what do I really mean by expand? We want to write this as the sum or difference of logarithms. Okay, the sum or difference of logarithms. That's what we're going to do here. Natural logarithms in this case. So that's what I mean by expand. Now we can't have multiples of logarithms. The rule is you can't have you could have like a 3 in front of one of your logarithms. So like 3 times the natural log of something, but you're not allowed to have an exponent on the input in the logarithm. Okay, so you're not allowed to keep the natural log of z cubed anywhere. You got to bring that 3 down in front, and that's just the rule when we say expand. You're going to write it as a sum or difference or multiple of logarithms, but no exponents. Okay, so when you look at this thing, look at the argument. The argument is the same as saying the input. Look at the input. There's lots of operations going on here. There's cubing, there's square rooting, there's multiplication of x times y, and there's division. But which of those operations is global in the sense that it affects everything? The division. It's a quotient. The argument or input is a quotient. That's what you need to see here, because that's what tells you what rule to apply first. Does the orange show up? Yeah, the orange shows up a little better than the yellow. Okay. So you would think of this as a quotient, and why is it so important to identify that kind of global operation going on in the input? Because it tells you to apply the quotient rule first, right? Now, why can't you apply, say, the power rule?
Because it's a fractional multiple.
Well, yeah, you're on the right track. But the main reason is this exponent of 3 only applies to the z. In order to bring the exponent down in front, that exponent of 3 would have to be on the entire quotient, and it's not. Does everybody see why you can't apply the power rule? You can't bring down that 3 yet. Same thing with x times y. I mean, that x times y is stuck way deep inside a square root on the bottom of a quotient, right? So you can't apply any kind of product rule yet. So the only operation that applies to the entire input is the division, the quotient. Okay, quotient rule, QR is what I'm applying. QR. So what would this look like once you apply the quotient rule? Natural log of z cubed minus ln, not 1 over, but just square root of x times y, right? Does everybody see that? Compare that with the generic form of the quotient rule. What does the generic form of the quotient rule say? It says that log base a of m divided by n is log base a of m minus log base a of n. So what's acting like the m? Z cubed, and what's acting like the n is this denominator of the square root of x times y. So log base a of m minus log base a of n becomes ln of z cubed minus ln of square root of x times y. Does that make sense? Everybody okay with that? All right, so again, we're expanding this as much as possible. So what now can I do with the natural log of z cubed? How can I rewrite it?
3 ln z.
3 ln z. Now, I'm not done over here, but what rule did I apply there?
Power rule.
So that's power. There's going to be a couple of different rules here, so I'm just going to, you don't have to keep track like this, but I want the notes to make sense, so I'm going to keep track. So that's the power rule, but I won't apply any other rule here except to an algebraic rule. How can you think of the square root of x times y using an exponent? So natural log of x times y to the 1/2, is that the right way to write it? We need parentheses around the x times y. And then what rule can I apply once again in the next step? The power rule, once again, I'm just gonna rewrite 3 natural log of z, that guy's done, minus 1/2 natural log of x times y. Notice I dropped the parentheses now because I don't need them, but if you don't want to drop them, you don't have to. Okay, you can put them back in there like I just did. Is it expanded as much as possible?
No.
No, because what can I do with the natural log of x times y?
You can use the product rule.
Okay, so in this step, we're going to use the product rule, so that we'll have to abbreviate product, PROD rule. And so this guy in front's going to stay the same, 3 natural log of z minus what? Oh, we're going to write a single number as a sum, right? Natural log of x times y is a sum. So what should I put after the 1/2? After the minus 1/2, maybe a set of parentheses, right? Because we're going to have to distribute that minus 1/2. And then how do you rewrite the natural log of x times y according to the product rule? Natural log of x plus natural log of y. Any explanation needed there? Is that okay? So m is like x and n is like y from the product rule. All right, and then the next part's just algebra. I'm going to distribute the minus 1/2. What does that give me? 3 natural log of z minus 1/2 natural log of x minus 1/2 natural log of y. And now it's expanded as much as possible. What's the opposite of expanding? Condensing into a single logarithm. Being able to condense into a single logarithm is going to allow you to solve logarithmic equations. There's one thing you have to do first when you go the other direction, and that is apply the power rule. Why? Well, okay. I don't want to say absolutely every time, but generally you want to apply the power rule first, so that you get the same number in front of each logarithm. Because you can't apply like the quotient rule or the product rule if you don't have the same number in front of the logs. So I'm going to say this, apply power rule first to each logarithm. And that's when you're condensing into a single logarithm. Okay. So if I do that, what's 2 log of x? Oh, by the way, when you see log of x, that's called a common logarithm. It really means log base 10. And as you guys probably know, your calculator will compute natural logarithms, ln x, whatever x is, and log of x, right? So if you need a decimal approximation, you can use your calculator to get it for those log functions. Not necessarily, depending on the calculator, if the base is different, your calculator may not compute it directly. So, okay, rewrite 2 log of x for me. What do you get? Log of x squared. So again, the input is x squared, and the base, when the base doesn't show, it's base 10. So it's really log base 10 of x squared, but we don't write that when it's base 10. We just say log of x squared. What about, okay, you have a minus. Ignore the minus. Minus 4 log y. How could you rewrite 4 log y?
Minus log y to the 4th.
Minus log y to the 4th. And then plus 1/2 log of z. How could you rewrite that? Oh, good. Yeah, you could. And in fact, you don't have to do it right away, but the z to the 1/2 is definitely the square root of z. I'm going to leave it as z to the 1/2 for now. Now, it's 0, yeah. So this guy, I'll put in the plus 0 so you can see what I did. Remember we talked about that rule, log base a of 1, no matter what the base, is 0 because a to the 0 equals 1. Yeah. So I actually applied the power rule and that property from yesterday all in one step. Okay, now I usually just work it from left to right. You could do multiple steps at once here, but since I'm only going to do one example, I want to really go through it in detail. So let's apply one rule at a time from left to right. How could you rewrite the log of x squared minus log y to the 4th? What rule would you use? The quotient rule, now we're going backwards, right? If you go back and look at the quotient rule, this is it, right? We're going now, though, from the right-hand side and condensing to the left-hand side. So you have to identify what, on the left-hand side, what your numerator is going to be, what your denominator is going to be on the input. So we've got log of x squared minus log of y to the fourth, which is going to condense into a single logarithm. What's it going to be? Log of x squared over y to the fourth. And then we still have plus log z to the 1/2, and then I'm not going to write down plus 0 anymore. Okay, now you see two logs added together. Automatically, what rule do you think of? The product rule, but just like with the quotient rule, if you go back to the statement of the product rule, just like with the quotient rule, we're starting now on the right side and going to the left side, right? Which basically just says, hey, take log of your two arguments from the original multiplied together, right? Your two inputs multiplied together. So let's go back down and see what that would be for this one. So we're adding these guys together. So this becomes the log of what?
Log of x squared z to the 1/2.
Yeah, ultimately that's what it's going to be on top. But just to apply the product rule, wouldn't it be this argument, x squared over y to the fourth, times this argument after the LOG? So does everybody see it would be log? So what rule am I using here? I didn't actually write down my rules. Here I used quotient, QR. Rule, actually, to go down to here, I use that. And then here I'm using product rule. And then how would you want to rewrite this, though? If you think of this as z to the 1/2 over 1, it's really log x squared. As you said, okay, you already called it z to the, Rami called it z to the 1/2. He called it square root of z. So how about square root of z in the numerator as a factor times the x squared all over y to the fourth. And so that becomes the input. The change of base, I'm in a pirate mood. Let's not call it the change of base formula. Let's call it the change of base formula. That's pretty bad.
It's a hearty joke.
The change of base formula, matey. So what if you have a calculator that only computes natural log, which is log base e, and log log, which is log base 10? What do? You use the change of base formula. So let's say you want the base to be base a, but the base is currently base b. It turns out that this handy formula will work. The log base b of m is equal to the log, okay, the new base is a of m, divided by log base a of the old base. Turns out that's the formula. And students get this confused all the time, but in practice it's really easy to use this formula for computing numerical logarithms, and I'll show you that with this next example. So what that formula is saying is, here's a way to remember it. Everybody look up. Take the log of 23, divide by the log of 7. That's the way to remember it. So log 23, now what does that really mean? Log, what's the base? 10, divided by log of 7, but that really means log base 10 of 7. I don't know what that is. Let's practice that. What do you get? Anybody have a calculator handy? Let's have more than one person do it so we can check ourselves. 1.61 approximately. Now, somebody try it with ln of 23 divided by ln of 7, and you'll get the same thing, won't you? Okay? So calculator-wise, is everybody okay with that? Why is it true? Because we said so? It works on my son. Because I said so. Doesn't really work. But why, he'll say. So can I prove this? Can I remember how to prove it? Yeah, I like proofs. I know you guys don't, but I do. And I have to entertain myself once in a while, right? Proof. Let's set y equal to log base b of m. So I'm setting y equal to the left-hand side of the statement of the change O base formula. What's the only thing we know how to do? Convert. So if we convert this to exponential form, can you guys tell me what you get? B to the y equals m. Okay. Now, I'm going to use a property we haven't formally talked about yet, but it should intuitively make sense to you. It should be true that if b to the y equals m, if we insert both sides into the log base a function, it should still be true, right? So long story short, you guys, I'm talking about taking the log of both sides. But you have to be really careful when you first explain that to students, because what does it look like I'm doing? I'm going to take the log base a. What does it look like I'm doing to somebody who's in beginning algebra? It looks like I'm multiplying both sides by log. Am I? No, that's not even possible, because log is not a number. You can't multiply by it. What I'm really doing is I'm inserting both sides into the log function and making the b to the y and the m inputs in that function. But certainly if b to the y equals m, then the function, the log base a of b to the y should equal log base a of m, because they're the same inputs, right? Does that reasoning make sense? Okay. Well, then we have it, believe it or not, because what rule can I apply on that left-hand side with that exponent? The power rule. And I get a product. I get a product of y times log base a of b equals log base a of m. And if I want to get y by itself, what can I do to both sides? Yeah, now this truly is division, because log base a of b for any particular a and any particular b is a number, and I can divide by numbers. And that's actually it. You get y is equal to the right side log base a of m divided by log base a of b. But remember what y was. Y is that original left-hand side. And we got the right-hand side we were interested in. So we're done. Another proof that hinged on converting from one form to another, right? In this case, exponential form to logarithmic form. And we got it. So that, knowing that, how to convert between forms is, I can't tell you how important that is. Vinegar has a hydronium ion concentration of 1.26 times 10 to the negative 3 mole per liter. I would think it'd be moles per liter, but I guess not.
There's mole and moles.
Is there?
It's mole is with a capital M, moles is with a lowercase m.
And the mole with the lowercase m is the little animal that's crawling around in my dirt in the backyard?
They're different measurements depending on, and they have a specific number too, mole and moles.
So they are actually different.
Yeah.
Interesting. Okay. Determine the pH of the vinegar and state whether the vinegar is an acid or base. So you guys have to remind me. There's a scale, I think it goes from 0 to 14, and 7 is right in the middle. So if it's less than 7, is it an acid or a base? Acid. If it's more than 7, it's a base. All right. And that's in the book, by the way, if you can't remember that. So basically, this is a plug and chug formula, right? So what are they giving us, pH or H+? H+. So we're going to just plug in H+ into that formula, negative log H+. And that's all it breaks down to. So the pH is going to be equal to negative log, okay, 1.26 times 10 to the negative 3. So I would go negative, okay, log is right on the left-hand column of buttons, right, kind of in the middle. 1.26 times 10 to the negative 3. Yeah, if you wanted to, you could just divide by 1,000, right? Same thing. And then, what do we get? I don't know how much, it didn't say where to round. I'll say 2.9. So 2.9, the pH is 2.9, and that means this thing is an acid. 80 out of the book gives you the pH, 5.6, which I guess is still an acid, right? And they want you to determine H+. So what's the formula? pH is equal to negative log H+. You guys fill it in for me. What am I filling in? Okay, you're given a pH, so you're asked to find the moles per liter, right? So 5.6 on the left side equals negative log H+. So this is a very simple logarithmic equation. And I'm going to tell you guys tomorrow, wait, is today Thursday? I'm going to tell you guys not tomorrow. I mean, I could try and tell you, but that wouldn't work very well. How about Monday? One technique for solving log equations is to try and get a single log on one side and a constant on the other. And that's the technique we're going to use here, because it's really easy to get a single log on one side. We almost have it. How do you get rid of the negative? So I'm going to divide out the negative, divide by -1, multiply by -1, same difference, and switch it around. I get log of H+ is equal to 5.6. Negative, yes. Does everybody see what I did there? Now, can we convert this to exponential form? What is the base of this logarithm? 10. So can you convert that for me? What do you get? Oh, careful.
10.
H+ equals 10. The base of the logarithm, the subscript in the logarithm, is the base of the exponent, and the exponent's all by itself. And so you're not going to write the answer that way. You're going to plug it in your calculator, go 10 to the negative 5.6, and get, okay, this notation means we'll go to a couple places just for fun. 2.51 times 10 to the negative 6. So 2.51 times 10 to the negative 6. What units are we in? Yeah. Make sense? I'm going to let you guys go a whole 2 minutes early.
Wow.
Make up for the 2 minutes late last time, right? See you guys later.